Hi, welcome to a special episode of C and Software Tools class. I have to travel for 1 week during the semester, so I'm recording these lectures so I can post them online and you can watch them and stay caught up with the material without us having to meet in person. So this is the recording for Lecture 8. This is where we're going to talk about pointers, and pointers are a piece of C syntax that we didn't really have in Java. We've got references that are a little like pointers, but C lets us work directly uh, with pointers, with the memory locations where things are stored. And using that, you can do some things that can be awfully convenient. So let's talk a little bit about how things are stored in memory and what we mean when we talk about the address of something in memory. So on this slide, I made a picture that shows how you can think about memory being organized. Memory is available in these little fixed size pieces called bytes. A byte you can think of as storage for a small number, for a value between 0 and 255 is one way to look at it. And when we've worked with the character type in C or the byte type in Java, that's a type made to let you talk about one of these little locations in memory. So storing something in memory, if you just had to store a single character in C, you might store that using a single byte. If you needed to store something bigger, something that wouldn't fit just in a small number, uh, a number with the range 0 to 255, you could use multiple bytes together. For instance, when you're storing an int, we've said that's a 4-byte quantity. So to store an int, the compiler will usually take 4 consecutive bytes in memory, and it'll store part of that int across each of those 4 bytes. And then that lets it effectively have a much bigger range than you would have with just any single byte. For bigger types like a double, that needs, at least on the common platform, that needs 8 bytes together in memory. And even things like the code of the functions in your program, those are stored in memory as a sequence of low-level machine instructions, one after another. So code for main might take hundreds or thousands of bytes, depending upon how big your main function is. Now, each of these bytes in memory has what's called an address. It's a number that identifies where that byte is in memory. And here in this picture, I'm pretending that my addresses for bytes start at 0. So maybe this is byte number 0. This is the next byte, that's byte number 1. And if we keep counting up, you can see this would be byte number 15 here and then 16 here. When we talk about where something is in memory, we call that its address, and we're usually talking about where it starts in memory. So this int, for instance, needs 4 bytes. But if you were wanting to keep up with its address, you'd keep up with the address of this first byte. So we might say its address was 16. And we could do that, and the compiler worries about that with everything that's being stored in memory. When you write a piece of code, like here I picked something simple, A gets B plus 1, you don't have to worry about you don't have to worry about where A and B are stored. But to write instructions for this, the compiler has to figure out where it's going to store those variables, and the instructions that operate on those variables have to use those memory locations. So this might compile down to instructions that say something like, well, go get the integer that starts at address 26. That'd be the value of B here. And then once you have a copy of that, you can usually do, or at least the processor in your computer can usually do basic math on that. So you could add 1 to that. And then to store the result in A, you would copy that to wherever A is stored. So here we're pretending that starts at address 12. So I'm trying to make the point that the compiler is already having to keep up with where everything is in memory for your program. And normally you don't have to worry about that, but you can if you want to. C gives you operators in the language that let you find out where things are stored, so get the addresses of things, and change the contents of memory based on addresses. So that's going to give us another way of getting at the contents of memory, the stuff in our variables, via addresses rather than just using the names of those variables. And this can be kind of handy. I'm trying to show some examples here of where this is useful. One way we've been using it so far, even though we haven't talked about it that much, is when we do pass by reference. Normally, when you pass something by value, when you call a function, if you want to give it a variable like x, if you're doing pass by value, the function gets a copy of what's in x. So if x was a 5, it gets a copy of that 5. And that's useful, but sometimes it's more useful for the function to just be told where that variable lives. So how about if instead of giving a function a copy of what's in my variable x, I tell it the memory address of x. It can still find out what's in x. It just has to look at that memory location. But if I know where that value lives in memory, I could also go in and change it if I wanted. And underneath, this is how pass by reference works in C. The syntax we've been using when we pass something to scanf and I've said that's pass by reference, that's really using this syntax for working with pointers. Being able to use pointers is useful for a couple of other things. I've listed them here. If you know where something is in memory, you can figure out the address of nearby things. And some things like arrays are organized as a bunch of values, one after another in memory. So knowing the address of one of those values would let you get to other array elements, or it would give you another way of getting to those array elements. And a few lectures from now, we'll see that being able to work with addresses will let us go to the C standard library and ask for memory. There's what's called dynamic memory allocation, and that lets you ask for however much memory you need to store something while your program is running. But the way you work with that memory is going to be through pointers. So learning how to do this will pay off later when we have to do dynamic memory allocation. When you're working with pointers to a value rather than just copies of that value, we've called this reference semantics. So value semantics is when you give a copy of a value. Reference semantics is when you tell where that value is stored. You'll also hear this described as indirection. Instead of telling you a thing, I tell you where to go get that thing. And for some of the reasons we just talked about, indirection can let you do more with a value than just look at it or compute new values from it. So to work with pointers in C, we need 3 operators that we never used in Java. Let's talk about them. So the first one is the address of operator. I said that in C, if you ask the compiler, it'll tell you where things are stored in memory. And here's how you ask it. If you put this ampersand symbol in front of an expression, like I'm showing here in front of a variable, it'll give you the it'll give you the address of that variable. So normally if you had a variable A, if you just said A, you'd be talking about the thing stored in A. What's its current value? But if you say ampersand A, then you're asking for the address of A. Tell me the memory address where A starts. So here's how you get addresses for things. This is called, I think I said this is called the address of operator. And we'd say it's a unary prefix operator. That just means unary means it takes one operand and it goes in front of its operand. So kind of like typecast would be another example of a unary prefix operator. Size of, address of operator. It takes one operand and it goes in front of its operand. So here's how you find out the addresses of things. But to work with addresses, you might need to temporarily store them. You need something that holds the address of something else. So to do that, we're going to need a new type operator. We don't see new type operators that much. Often we're using operators that compute values. But type operators are operators that go into describing the type of a thing. Like when you want to make an array, you use square brackets. In Java, you can use square brackets without anything in them. And I would say that's a type operator. That's how you define a variable that can hold a reference to an array in Java. In C, star can do the job of a type operator for defining pointer types. This lets us make variables that can hold the addresses of other things. The way you use it is you put a type of something in front, and then a star, and then the name of a variable that you, well, let me try and describe that better. To use this operator, probably the most common way to do it is when you're declaring new variables. So like I just said, you give the type, you give the star, and then the name of that new variable. And then that variable will be able to hold the address of whatever that type is. So maybe an example will make this easier to talk about. Here, if I made a variable a like this, its type is int. It can hold an integer value between about -2 billion and +2 billion. If I make a variable like this, well, this is the syntax I'm talking about. This PTR can hold the address of an int. PTR can hold a pointer to any int variable. Well, if you declare these variables like this, I haven't initialized them. So this variable a, if it's a stack variable, I don't know what it's going to contain. If this is a pointer, I don't know where it's going to point yet, or I haven't made it point to anything. But if I use that operator we just talked about, that's how I can store something useful in this pointer variable. So this says, give me the address of a, and then put that in this pointer variable. PTR is made for holding pointers to ints, for holding the addresses of ints. So this makes it point to this particular int. So it holds the address wherever A is stored. This lets me find out that location and temporarily store that in a variable. Well, I guess the next question would be, if you had the address of a thing, what could you do with it? We need one more operator for this. And this is, it's not a type operator, although it's written the same way. This is just a different job that star can do. So on our previous slide, I was saying star, you could use that to define a new type. But if you put star in front of a pointer, then we call it the dereference operator. It's also a unary prefix operator, so it just takes one operand, and it comes before its operand. In front of a pointer, star gives you the thing it points to. So if we did what was at the end of the previous slide, backing up, if I got the address of an int a, and I stored that in this variable PTR, if I dereference that, if I say, give me the thing PTR points to, this would be the value of a, at least if I, across these two slides, if I took the address of a and stored it in a pointer, and then I said, give me the thing that pointer points to, I would be getting to the contents of a. So this gives me another way of getting to the values of variables via their addresses. Star, so we've learned two operators for working with pointers, plus a type operator, star and ampersand, and they kind of do the opposite. They're kind of inverses of each other. And often you'll be using ampersand to get the addresses of things, and then star, the dereference operator, to get the thing that that address points to. And that's what I'm trying to show here. For anything, and by that I mean maybe a variable, maybe an element of an array, if you put an ampersand in front of that, you're going to get the address of that thing. And you can store that in a pointer variable. So ampersand you can think of as saying, give me the address of this thing. Star in front of a pointer kind of goes the other way. It says, give me the thing that this address points to. You can use this to get a copy of a value that the pointer points to. So this would take whatever that pointer points to and copy it to another variable. Or you could use this to change what's in that thing that the pointer points to. So you could take some other value and put it in that memory using the dereference operator. So across these last few slides, I've introduced the three operators that we need. I made up some examples to try to talk about this and to try to sneak up on some useful things we could do with these. So far, we've mostly just been learning syntax, and this is really going to help us make sure we understand the syntax before we start doing useful stuff. So here, let's pretend I make a couple of integer variables, a and b, and pretend they go here in memory. So A is stored up here, B is stored down here. Then I put values in each of these variables. So you can think of A as holding a 1 and B holds 5. And then I make a pointer variable that can hold the address of an int. And I started out holding the address of A. So like I'm trying to show in my picture here, well, an address is just a number. So I just made up this picture. But if you think of A as starting at address 12, then when you get that address and store it in a pointer, that pointer is holding the address of that thing. But often, instead of thinking of the particular number that is an address, I just made up this address here. Instead of worrying about the particular number, it's often more useful to think of the pointer as pointing to that thing. Internally, that means it holds the address. But this little red arrow I drew is, for me, often an easier way to think about that. So pointer holds the address of A. It's another way of getting to A. And when I do this initialization here, that's what sets it up so that it starts out holding the address of A. I said, give me the address of A with the address of operator. I made a new variable PTR that can hold the address of any int, and I set it up so it holds the address of A. Once I have that address, I can use that to sneak in and change the value of A. That's what I'm doing here. So I just added a line here, and I'm showing I could take a 10, and I could put that wherever this pointer points. So this star PTR, you can think of that as saying, go to the thing this pointer points to. Now, because of this previous line, that's still A, and put a 10 there. So that erases the 1 that used to be stored in A and stores a 10 there instead. So here I'm trying to show, well, if you add a pointer to a thing, you can use that to change that thing. You can replace what's in A by getting to that via this pointer. You can make a pointer point somewhere else. It's like, unless you say otherwise, it's like any other variable. So you could change the address stored in a pointer. And that's what I'm doing next. I say, take PTR, and I know it was pointing at A, but make it hold the address of B. Take the address of B and store that in the pointer. And now if you think of pointer as holding a numeric address, well, here I'm pretending B starts at address 26, so I changed that. But for this arrow, I just made it point to B instead. Like I said, that's an easier way for me to keep up with that. So now pointer holds the address of B. A and B are both ints. PTR can hold the address of any int, so it doesn't have to stay pointing at A forever. I can make it point somewhere else. And now pointer points at B, and I could use it to change what's in B. I guess for these last two lines, notice the difference is the star. When I put a star in front, I'm saying go to the thing PTR points to and change that. But without the star, I'm just changing what's in the variable PTR. I'm making it point somewhere else. And one more example, like I said, if PTR is pointing at B now, I can say, well, take PTR, dereference it. So I want to talk about the thing it points to that was a 5. But if I increment that, if I put a plus plus in front, that's going to take that 5 and turn it to 6, like I'm showing in my picture. So a nice thing about a pointer is they don't have to stay pointing at the same place. You can move them around, and then you could potentially, I mean, we're not doing that here, but you could potentially use the same code to change different things in your program by using pointers to those different things. So it gives us another alternative for how to update variables or other storage within our program. So this was mostly just playing around. It's 2 ints and a pointer. To continue playing around with the syntax, we can make, here I'm showing off a couple of pointers and 2 variables. I make 2 variables, A and B. Here I'm not, I mean, back here I drew them as if they live at particular memory addresses. But if I'm just going to use arrows to show where my pointers point, I don't really need to do that. I can just say, well, A and B live somewhere in memory. They start out with these 2 values. After I've made A and B, I make a couple of pointers. I called one of them PA. It could hold the address of any int, but I make it start out holding the address of A. So I think of it as pointing to A in memory. And I do the same thing for PB, but I make it hold the address of B. Then I start messing with these pointers, and we'll talk through that a sort of a case at a time. So first, I take PA, I dereference it and add 1 to it. So you can think of that as saying so take PA, go to the thing it points to that was a 5, but I said add 1 to that, so that 5 is going to turn to a 6. What do I do next? So I'm pretending that this code runs one statement after another. Well, next, I do the same thing with PA. Give me the thing PA points to. So that'd be the 6 up here. Take that and add it to whatever thing PB points to. So PB is pointing to this 10, and I'm adding this 6 to it. So that's going to take that 10 and turn it into a 16. What do I do next? Well, here I'm taking PA and I'm copying it to PB. I didn't put a dereference in front of either of these. So that's just going to copy whatever is in PA. That's the address of an int, and it's going to copy that over PB. So PB is going to get that same address. I didn't use a star. I'm not talking about the things these pointers point to. I'm just copying the value from one pointer to another. I'm copying whatever's in PA into PB, so that would make PB point to the same thing as PA, like I'm showing in this slide. Now PB points to A. It got a copy of the address that was being held by PA. And then my last example, just to make sense of these slides, I colored red the part that each slide is showing. I usually am starting to talk about the next slide before I switch to it, so that when we switch to it, you can kind of see what I just talked about. So what happens next? Well, I take whatever PB points to. That'd be the 6 up here. It's pointing to A. And I add 4 to that. So that's going to take this 6 and turn it into a 10 by adding 4. All right, we've been playing with sort of our first examples of pointers. We've really only been using ints so far, but it's worth knowing that every type can have its own pointer type. And the type of the pointer matters. So here I made a char C. You can make a variable for holding the address of a char and make it point to C. Same thing, if you've got a float F, you can make a pointer that points to that float. Notice that the type of the pointer depends on what kind of thing it points to. So a float pointer, I would declare as this variable is a pointer to a float. I can have shorts, I can have pointers to shorts. You could even have pointers to other pointers. A pointer is a type. So if you wanted to hold the address of a pointer, that would be a way of looking at that pointer or changing it via its address. I got a few examples that show this off, and we will use this trick. It's awfully useful. So this is really just to get us ready for that. We'll use it, but it'll be a few lectures before we use it very much. But here, to show off what I just said, you can have pointers to anything, including other pointers. This is kind of like the example we saw before. I just added more stuff. So I made a couple of int variables, A and B, just like before. I made a couple of pointers to ints, PA and PB, and made them each point to A and B. And then I made a pointer to those pointers. So I took the address of PA. That would be this variable here. And I want to hold that in a pointer. So I would need a pointer to that pointer to an int. So this variable PPA is the right type. You can read its type as PPA is a pointer to an int. Same thing with PPB. It holds the address of a pointer to an int, so it's got the same type, pointer to int. So these 6 declarations set up my variables and pointers so they look like this. Let's talk about different things we could do with these based on where they point and their types. First, let's just try changing, well, this is really going to change A. I'm going to take a 15. What do I want to do with that? Well, I want to take PPA. That's this thing down here. I want to dereference it. So you could read this as take PPA, use star on that. So dereference it. Go follow this pointer to the thing it points to. So after this star, I think of this as the first one because it applies to PPA. So dereference that. Now I'm talking about the thing it points to. So I'm talking about PA. What do I do with that? I dereference that. So I follow this pointer and that gets me up to this 5. But I want to change what's in that 5. I want to put a 15 there. So this follows a pointer. It follows the pointer that points to, and it puts a 15 there. Let's try a different example. So forget this last line, keep all the same initialization. But now let's try these two things. So this isn't continuing from the same example. We'll pretend we start out these 6 variables the same way, but instead, let's take PPA, let's dereference it. So that's starting from here, follow this arrow. If you're dereferencing this, then you're talking about the thing PPA points to. You're talking about this pointer. What do you want to do with that pointer? Notice here, I only dereferenced it once. The previous example, I followed a pointer and then I followed the pointer from there. Here, I'm just taking PPA, I'm dereferencing it once, so I'm getting this pointer. What do you want to do? I want to set it to the address of B. So that's going to make this hold the address of B. It's going to make this pointer point to B. Then what do? I'll go ahead to the next slide because it shows how the pointers change. But then after I've done that, I take PPA, I dereference it and dereference it again. But since I moved this pointer, now I'm up here at B. I want to take that, well, that was a 10, but I add 1 to it, so now it's an 11. So because I moved this pointer before I did the dereference here, after I do that star, I end up here at B again, because this pointer has changed. All right, one more example, throw away those last 2 lines, and let's try moving a different pointer. So same setup, but I'm going to take PPA, and I'm going to make it hold, sorry. Yeah, apologize. I accidentally bumped 2 slides ahead. So we're replacing the last 2 lines, same initialization, but the first thing I'm going to do is get the address of PB. That's this thing here. And I'm going to store that in PPA. PPA could hold the address of any pointer to an int. I want to make it point to this pointer to an int. So this first line moves PPA like this. And then the second line, it's almost the same line as before. I say take PPA and dereference it. So that gets me up to here. Dereference that again, that gets me up to here. This was a 10, but I subtracted 1 from it, so now it's a 9. So this, again, we're still playing with the pointer syntax, but with the same basic ideas. We can come up with more interesting connections between pointers and really alternative ways of changing the data within our programs. Now, one detail that I haven't talked about until now is the scope of these type operators. If you declared, let's say you wanted to make 2 variables like X and Y, if you declare them like this, X is a pointer to an int, Y, well, it's just going to be an int. It doesn't get, so when you're declaring multiple variables like this, the type over here at the left applies to every variable, but the star doesn't. That's kind of unfortunate. I wish the language wasn't like that. Seems a little inconsistent to me, but it's worth remembering that if you want Y to also be a pointer to an int and not just a plain old int, you need to repeat the star part. So that's why, that's why most people, when they declare pointers, they do them more like this. I've been putting a lot of spaces in my declaration, but often you'll see people write the star right up next to the variable name. It's not part of the variable name. Here, this variable is IP, but putting the star right next to it maybe helps remind us that the star just goes with that one variable. All right, what I'm really talking about on this slide is one special pointer value null. Null is, it's not a reserved word in the language. It's a preprocessor defined constant, but it is kind of does the same job as the null reference in Java. It's a pointer value that you can assign to any pointer type. Uh, and it means this pointer doesn't point to anything. It's a way of marking a pointer with, well, a value that indicates it doesn't point to anything. It internally, it's implemented with the value 0, kind of like its name suggests. So when you set a pointer to null, you're really giving it the address 0. For that to work, we kind of have to agree, well, we won't store anything useful starting at address 0. At least if we did that, we couldn't really tell the difference between that thing and a null pointer. So we'll use null, we'll use that pointer value of 0 to indicate this, to mean this pointer doesn't point to anything. The nice thing about using for the 0 for this is we can also use it as a truth value. You could think of checking a pointer to see if it's null. That would work fine in a conditional like I'm doing down here. And since 0 is automatically treated as false, if a pointer has a value null, it'll evaluate to false. So you can think of this as saying, does this point to anything? It's fine to look at the value of a pointer that may be null to see if it's null or not, like I'm doing here. You just shouldn't dereference it. Same in Java. If you dereference a null pointer, if you try to follow that pointer and access the thing it points to, well, in Java, that's going to throw an exception. In C, that might crash your program, but technically the behavior is undefined. If you follow a pointer that doesn't really point to anything, who knows what you're going to get? It'll probably be bad. It'll probably crash your program. If you were trying to debug it, I would kind of want it to crash my program immediately so I could fix it. All right, so we'll use null pointer as a way of marking pointers that don't point to anything. And like I said, any pointer type can be assigned a value of null. That's what I'm showing in these two first lines of code. All right, so what are pointers good for? Like I said, we've been using them for a little while without making a big deal out of it. They are a handy way of doing pass by reference. The trick, and you'll recognize that ampersand that we learned is the same thing we've been using to pass parameters to scanf. So that scanf can not only look at that parameter, but it can change what's in that any variable that we pass in. Knowing the syntax for this means we could write our own functions that take values passed by reference. We're not, there's nothing special about scanf. We can use the same syntax, and that's kind of what I'm showing in this next example. So let's say we wanted to write a function that, given two integer variables, swaps them. So it takes let's say it's given variables x and y, and it swaps what's in those two variables. If all we had was passed by a value, we couldn't do this. A function, it would get the value of those two variables, and it could change them inside the function. But as soon as it returned, the values of those variables would be unchanged because the function just had copies of them. But how about if we write the function like this? Instead of expecting two integers, let's define it so it takes the addresses of two integers. That's what swap, the way I've defined it here, does. It wants an address of an integer that it's going to call x, another address of an integer that it's going to call y. When you call this function, well, its parameters are expecting addresses of integers. So you have to pass the addresses of integers. You have to have maybe a variable a and b that are both type int, and you got to put the ampersand in front of those. If you didn't, the compiler is going to complain because the types don't match. So you'd have to call the function like this. This is a little bit of a disadvantage. You need a little more syntax to pass the address of a thing rather than just giving a copy of that value. So let's say we get the address of a couple of integers, a and b. I showed over here how you could think of this in memory. A and b are stored somewhere. Inside this function, x and y are just holding the addresses of these two things. If I know the addresses of these two things, I can go in and change what's in those two variables. So I get whatever's in a by dereferencing x. That'll give me this 25. I copy whatever's in y, whatever whatever's in B, whatever Y points to, into whatever X points to. And then I take my saved copy of what was in the first parameter and copy that into whatever Y points to. So this, using a temporary variable, this does the usual trick to swap the contents of two variables, but via pointers to those variables rather than just via copies of those. Here I'm showing that you could make functions that take pointers instead of integer values. You could mix this. Just because you have some pointer parameters doesn't mean you couldn't also have some non-pointer parameters. I made up a function for this. Let's say you want a function clamp that takes one integer passed by reference, so by address, and another integer that's just passed by value, let's say bound. And the job of this function is pretty simple. If the value of the first parameter is bigger than bound, I'm going to pull it down to that value bound. So this is a maximum I want for whatever this first parameter points to. Inside the function, I look at the value x points to, and if it's too big, I can use dereference to go in and change that value. To call this function, well, my second parameter, I can just pass in any integer value I want there. So like a literal value would be fine, but I need to give the address of an int for the first parameter. So in a function, my point is you can take a mix of pointers and values that are passed by value. I would say only use pointers where you need to pass something by reference. Whenever you're passing pointers to a function or in general using pointers, you need to make sure they actually point to something. An easy mistake to make with this same function would be, well, it's expecting a pointer to an int. So let's give it a pointer to an int like I'm doing in this bottom piece of code. It needs an integer parameter, so I made a variable b to pass in as the integer. It needs a pointer to an int parameter, so I made a variable p to pass in as the first parameter. And this would compile, but it's probably not going to do what you want. This parameter or this variable p is a pointer, but I didn't make it point to anything. I just declared it and I never gave it any address. So in this picture, I'm trying to show that it's an uninitialized pointer. Just like a stack variable that you never put any value in that, who knows what its value is going to be for a pointer variable. And if you didn't make it point to something, who knows what address it contains. That's going to be a problem when you dereference it. But here I never dereference it directly. I just make it someone else's problem by passing that to this clamp function. So when it wakes up, it gets a pointer that's just a copy of my uninitialized pointer. And when it tries to dereference that, when it tries to either look at what that points to or change the value it points to, that's probably going to crash my program. An uninitialized pointer, kind of like a null pointer. Whenever you try to use it, it's probably, it probably doesn't really point to the thing that you said it's supposed to point to. So when you try to use that pointer to get to something, it's probably going to be outside of the memory that your program is permitted to use. So that would crash your program. Here we're talking about pointers as parameters to functions. You could have a pointer as a return value from a function. I just made up an example for this. Let's say you've got a list of integers and you want to be able to look up values in that list. I could make a function that does that, but instead of just giving you a copy of the value in the list, which would be kind of silly. If I say, is there a 5 on the list, and you return 5, well, I already gave you 5 as a parameter. There's no value in you just giving me back a copy of 5. But if you gave me a pointer to the right element of this list, that would let me change that element if I wanted. And that's kind of what this function does. You give me a value, I'll go look through the list, and if I find the value you told me you wanted, I'll return its address. It's stuff that we've already seen, but this is the first time we've gotten the address of an array element. I looked up element I in my list, and then I said, give me the address of that. So this will return, an array of ints is just a bunch of ints, one after another in memory. This goes and gets one of them, and then it's okay to say, give me the address of just that one thing. It should be a pointer to one of those ints in the array. And that's what this function says it returns. Notice I also had a plan for what happens if I can't find the value that you asked me to look up. And that'd be a good job for a null pointer. That means this pointer doesn't point to anything. So I could use that to handle the case where there was, you asked me to look up a value 5 and maybe it wasn't on the list. So this works just fine as an example of how to return a pointer. You could have a function that looks up something and then gives you its location. You can also try this, but this would be a bad example. Here, a simpler example, let's say I give you 2 ints, or let's say I want a function. I'm going to give it 2 ints, and then let's have it return the address of the larger one. So this seems like the type it should have. You get an int A and B, and you give back a pointer to whichever one's bigger. I look at the 2 integers. If A is bigger, I give you the address of A. If B is bigger, I give you the address of B. This would be a way you could use it, but this would be a way to probably crash your program down here at the bottom, or I would say it's an error, even if it, well, probably wouldn't really crash your program. The mistake I'm making here is inside this function, I'm returning the address of one of my 2 parameters. But parameters are just like local variables. They're stack allocated and they go away as soon as the function exits. So A is just a copy of whatever you passed in as the first parameter. B is just a copy of the second parameter. If I return pointers to those copies, as soon as I return, those copies go away. So whatever you do with this pointer up here in the caller is trying to access memory that's not really holding these 2 values or anymore. At least you're not guaranteed that it is. So this would be a bad way of returning a pointer from a function. Although backing up, there are perfectly legal ways to do it, like this example. Here I'm returning an address, but it's allocated out of this global variable. So that global variable should be around until the program completely exits. So it's okay for you to use that pointer, even if the function has exited. I guess there are other pointer mistakes. In fact, there are a lot of pointer mistakes you could make that we didn't have to worry about until we learned about pointers. Observe if I just made up an address. Addresses are numbers, so here I just made up a numeric address. I used a typecast to tell the compiler, pretend that's a pointer to an int. Well, I can do that, but since I just made up this address, probably not really a legal address of an int in my program. Probably, if I just made it up, it's probably not really part of my program's memory. So if you do this, this is probably going to crash your program. Typecasts are enough to make the compiler accept this code. It's probably still just a bad idea. You're doing the same thing here, even if it's not as obvious. If you make an uninitialized pointer variable, then it starts out with who knows what address in it. When you dereference that, you're kind of doing the same thing. You're accessing an arbitrary memory location, and that'll probably crash your program. Pointers are, we said they're holding numbers. They have their own types. The point I'm trying to make here is if you wanted to look at the value in a pointer, you can, and that might be useful for some debugging operations. They are numbers, but usually the compiler won't want you to print them like plain old integers. But there is a conversion specifier that'll print any type of pointer, and it's %p. If you print out a pointer like this, it'll show you the numeric address. It usually prints it as a hexadecimal number. You probably have seen hexadecimal before, but we talk about that in about a week. If you printed out a pointer, you might get a hexadecimal number like this, at least on a 32-bit machine. If you were on a more modern 64-bit machine, you'd still get a hexadecimal number. It'd just be a lot longer. And it's because when you describe a machine as 32 bits or 64 bits, you're really talking about the size of addresses on that machine. So on a modern 64-bit machine, pointers are usually going to show up as 64-bit numbers. So they'll be printed out with, 16 digits of hex. Again, knowing the particular numeric value of a pointer is not usually that useful, but you can tell some things like just looking at a pointer. You can probably guess whether that's in the stack part of your machine or is that a global variable. There's some other things you can tell like that. All right. We've seen that the C compiler is very lax about checking or really enforcing the types of numeric variables. And when I say it's lax, I mean it'll let you freely mix types. You can make a char, a float, and a short, and then you can just copy between them. And it knows what their types are, so it'll convert where it needs to, but it doesn't force you to use a typecast in these places. So it'll let you do these conversions freely. But it won't let you do that with pointer types. Here's kind of the same idea. I made the three variables of three different types. I made pointers for each of those types. So C pointer can hold the address of a character. Float pointer, it's fine to set that to the address of a float. Short pointer can hold the address of a short. But down here, I'm mixing them up. I'm trying to take the address of a char and put it in a float pointer, and the compiler's not going to like that. Same with these other two. So notice that even though the compiler is not very strict on the type of numeric expressions, it'll let you do a lot of things Java wouldn't. It is very particular on the type of pointers. And the reason for that is because even though all pointers are just numeric addresses, they're where something starts in memory, they don't all behave the same. That's what I'm trying to show here. Even though all pointers are stored pretty much the same, the way they're used is going to depend on the type of thing they point to. So here, I make a char, I make an int, I get the addresses of these two things, and C pointer is holding the address of a char, I pointer is holding the address of an int. I can use those pointers to change what's in the int and the char, and that's a good job for pointer dereference. So take the character that C pointer points to and put a J there instead. And that works fine. That'll replace this H with the letter J. It'll replace this 1 byte with a new value. If I do this with an int, though, ints are 4 bytes. So when I put a new value in this int through its pointer, I'm really going to be changing 4 bytes. And that's what I'm trying to say. When I use these two pointers, this one modifies 1 byte of memory at a time, and this one modifies 4 bytes. If you're willing to typecast, you can change which pointer points to which type of value. And that's what I'm doing here. I set up everything like we did before, but then I get the address of I and store that in the char pointer. That required a cast, but I can do it. I get the address of a char and I store that in an int pointer, and then the same 2 lines of code. But the problem is when I follow this int pointer and change what's in the memory it points to, it's still going to try to change 4 bytes of memory, which means it's writing out past the end of that char in memory, probably overwriting some other stuff, just like a buffer overflow. This isn't probably not going to crash your program, but it's probably still a bad idea. When I follow this char pointer, it's only going to change 1 byte of memory, even though the int that it's pointing to requires 4 bytes. So because what happens when you use a pointer depends on the pointer's type, like I'm trying to show here, the compiler's very uptight about mixing pointer types together. It'll let you do this, but you have to use typecasts to show, I guess, to claim that you really know what you're doing. Now with pointer types, because the compiler is uptight about this, there's some syntax that it's fine with, and there's some syntax that it's going to complain about, usually because it doesn't really make sense. And that's what I'm going to show over the next couple of slides. To talk through this, I made up a few variables. I've got an int and an int pointer, a double and a pointer to a double, a char, and a variable that can hold the address of a char. Pretend I set all of these up so they have meaningful values and they point to ints or chars or doubles as their type suggests. And then consider each of these statements. Do they make sense? What are they going to do? Is the compiler going to accept them? We'll go through them one at a time. Although if you want to cheat, you can look ahead at the next slide because it's got all the answers. But let's talk through this. So here, I'm taking a char pointer. I'm dereferencing it So I'm taking the char it points to, and I'm copying that to an int. Is that okay? I mean, the types don't match, but the compiler's okay with that. I'm just to make this work, it just has to take the char that this pointer points to and convert that to an int so it can store it in this int variable, and that's fine. But it's not going to like this. This is kind of what we were talking about before. I'm taking the address of an int and I'm trying to store that in a thing that's made for holding the address of doubles. So I'm trying to copy a pointer and the pointer types don't match. So the compiler is going to complain about this. Down here, well, I'm using a pointer to a double and a pointer to a char, but I'm taking that pointer to a double and getting the double value, the floating point number that it points to, and I'm copying that into whatever char value this pointer points to. To convert here, I would just have to convert a double to a char so I can store it in the char that this thing points to, and the compiler's fine with that. It'll convert the numeric values. It'll take the 8-byte double here, convert it to a char, and store it in the 1-byte char that this points to, and that's fine. But it doesn't like this last example, kind of for a different reason. Here, the types look good. I'm taking an integer pointer, so this is pointer to int, and I'm storing it in a thing, or I'm trying to store it in a thing that's also the address of an int. So the types on both sides are pointer to int, but the problem with this is you can't use address of something on the left side of an assignment. You can't change the address of a thing. You can get the address of a thing, but you can't tell the compiler, oh, now this thing's address is somewhere else. So this is, like I said, this is a summary of what I just tried to talk through. This is what's wrong with each of these. There are a bunch of other, I mean, just kind of trivia questions of, or examples of, is this okay? Is this not okay? These are all examples that make sense. Here, I'm just using integer types. So I made an integer variable A and B. I made a couple of pointers, P, X, and PY. And then we'll talk through a couple of examples of why these make sense. This takes whatever PY points to. Well, it's a pointer to an int. So this should be an integer value. Whatever py points to should be an int, and you're copying that to an int variable, no problem. Here you're just taking a constant, 35, and storing that in whatever py points to. Well, this is an int. No, I said py, px, whatever px points to. This is an int, and whatever px points to, that should be an int as well, so this assignment will work. Here I'm getting a value out of a variable, an integer variable b, and copying it into whatever integer px points to. That's fine. Here I'm doing the same kind of thing via two pointers. I'm getting whatever int py points to and copying that into whatever int px points to. No problem with that. Here I'm taking the address of b. Well, b is an int. So I'm taking the address of b, that's the address of an int, a pointer to an int, and I'm copying that to px, which is made for, I mean, according to its type, it's made for holding pointers to ints. So that's fine. Here, I'm just going straight between the two pointers. Take whatever pointer to int is in py and copy it into px. Now px points to the same place as py. So all of these, I tried to write short comments that summarize why all of these make sense. And none of these make sense. We went through all the previous examples, but we'll just do a couple here. Same types, but this first example won't work. Well, 35 is an int, but you can't take the address of a literal int. Variables and array elements have addresses, but just plain old numbers don't have addresses. So this won't work. Down here, well, 35 is a number, and pointers are really just numeric addresses, but unless you're willing to use a typecast, the compiler isn't going to let you use 35 as an address. So when you try to dereference that, it doesn't like just going to memory address 35. If you stuck in a typecast there and said, really pretend this 35 is a pointer to an int, that would work. But without the typecast, it's going to say that doesn't look like a plausible pointer value that you should be using. This is really doing the same thing. I'm just trying to do it via a pointer variable. Just like up here, it's not going to believe 35 is a reasonable memory address if I just use that as a number. And since I'm trying to copy it into a pointer variable, it's going to complain about that. Down here, the types don't match. B has an address, and addresses are just numbers, but it's not going to want you to just store that address in an integer variable. We've got pointer types that are made for holding addresses. For this example, we'll stop there, but you can read the rest of these and see if your intuition matches the short explanation on the right. We've been using our new pointer operators, but we haven't talked about their precedence. For dereference and address of, those are both treated in terms of precedence, like the other unary prefix operators. So they're in that second highest category of precedence. So up there with typecast and size of and pre-increment. So worth remembering that they have pretty high precedence. It's just this top category beats them. Array indexing, we haven't talked about it that much, but function call you could think of as a operator, and post increment and post decrement. For when we learned about pointers, we also learned about a new type operator. We've been using it all lecture. It's star for defining pointer types. So we've really got a small collection of type operators so far. And I wanted to practice making some stuff by combining some of those type operators. We know about all the primitive types like int and long and double. And we know about pointer, star, for making pointer types. And we already knew about array or square brackets for making arrays. So we could start combining these things like, P declared like this is, well, this is easy. It's a pointer to an int. A is an array of ints. PP down here would be, well, it can hold the address of an int, or said a little bit differently, it would be a pointer to an int. We used an example like that earlier. But how about this? Here I'm mixing the two type operators. So AP, it's an array, but it also says it's a pointer. Is it an array of 10 pointers to ints, or is it a pointer to an array of 10 ints? Which of these has higher precedence when you're reading types? The good thing is, even though it's not what we were talking about, it still follows the same rules as this table. So arrays in types, or square brackets in types, are that highest category of precedence. Star, even though it's, well, here it's the dereference operator, and here it's the type operator for defining pointers, it still follows the same precedence. So there's really only one rule to remember there. So that tells me the square brackets go first in reading the type. And in C, because you've got a small set of type operators, but there are interesting ways you can combine them. It's worth getting a little bit of practice reading the types of things. So the rule that I use, and I've been secretly doing this all lecture long, if you've watched what I've done with my pointer, with my mouse pointer, when I'm reading a type for a variable, I start with the variable name and I work my way out respecting the precedence of the type operator, those type operators. So for PP, you could read it, PP is a pointer to an int. And here I put in some extra space, but even if you did it like on this previous slide, it still has the same type. How about AP? Well, AP is, well, we got pointer on this side and array on this side, but we just said array has higher precedence. So unless you do something else, the compiler's going to read this as AP is an array of 10 pointers to ints. So it's an array that's got 10 slots, and every one of those is a pointer. Back here when we first started talking about this, I said it's either an array of 10 pointers or it's a pointer to an array of 10 ints. Well, unless you put in some parentheses to change the precedence, it's going to read this as AP is an array of 10 pointers to ints. Well, let me say one thing I forgot to say before. Back when we were talking about on a 64-bit architecture, pointers are 64 bits long. I'll go ahead and say that means storing a pointer would take 8 bytes on the common platform. So that would mean this array of 10 pointers would be an array of 10 elements where every one of them is a pointer. So every pointer takes 8 bytes. So this would take 80 bytes to store, 8 bytes for each of the 10 pointers. Let's see one more type operator. We learned about star. We already knew about square bracket, but it's more interesting now that we can mix it with some other type operators. Const can be used to define new types. Remember, it's a reserved word in Java, but they didn't really use it in Java. I think they originally planned to use it. But in C, const can be used to help define new types. And you can think of const as meaning, don't let me change the value of this thing during its lifetime. Let's talk through an example or a couple of examples. And then the reason we're talking about this now is const starts getting useful when you mix it with arrays and pointers. So let's talk about what it does here. So if you just made a variable a like this and you set it to 25, you didn't say anything about const. So the compiler will let you change this a later. Here, though, I made a variable b. I set it to a value, but I said make it const. So if you wanted to read const in a type, just like before, you can say, well, b is a const integer. It holds an integer, but I said it was const, so I'm asking the compiler to not let me change the integer that it's stored in. You can pick whatever value you want when it goes into scope, but you can't change what's in B later on. If you try, the compiler will complain about that. And this outermost const, the compiler will let you put it here between the variable name and the type, or you can put it in front. A lot of people put it in front, and that's fine. I tend to put it after this type because I think my reading rule works better for that. B is a const int. This means the same thing. C is a const int, but if you read it like this, you read C as an int that is const. And I think the rule works a little better like that. So that's one reason I usually do it like this. Notice that we got a perfectly good reserved word const, but we can't actually use it to define constant expressions. Remember, we said in a few places, like the cases on a switch, the compiler requires a const expression. And unfortunately, even though the keyword is const doesn't make const expressions, or variables that are const can't be used where const expressions are required. And this piece of code kind of shows that off. C has the word const on it, so inside each iteration of this loop, once I set C to be I plus 10, I can't change it. The compiler will complain. But it's not really a const. It gets set to a different value each time this loop iterates. So there's not one value that the compiler can figure out for C. So it won't let us use it in place of const expressions. I said const is really useful when you start combining it with array and pointer types, and that's what I'm starting to show here. I make 3 integer variables a, b, and c, and then I start making some pointers to those. X is a pointer to a const int. And I set it to point A. So that would let it hold the address of A. I can get to A, but I said it's a pointer to a const int. So that would mean I can't change the value inside the int it points to. I can't use X to change A. It holds the address of A. I can look at A, but I can't change it. So that means I can't do this. I can't dereference X and then put something else inside A. Because when I was making X, I said, don't let me do that. I want X to be a pointer to a const int, a pointer to an int that I can't change. I could make it point somewhere else, but I can't change, no matter where I make it point, I can't use it to change what's in the int it points to. Down here, I move the const, and it means something else. If you read it, y is a const pointer to an int. I didn't say anything about the int being const, so I can use y to change what's in B. But once I've made y, I can't move it to point somewhere else. So I can't do this. I can't say, well, now give y the address of C, because I said I want it to be a const pointer to an int. I can't make it point somewhere else. Down here, I put the const in both places. And now I've got a pointer to a const, sorry, Z is a const pointer to a const int. It holds the address of C. You can use it to look at C, but you can't change what's in C, at least not via this pointer. And you can't move the pointer to point to somewhere else. So you've made a pointer here where you've restricted a lot of what you can do with it. And that is a little bit weird. You might say, why would I want to make variables that I can't do things with? Variables that are less useful because I marked them as const. And the real reason for that is in function parameters. It's not really about making it's not about making a variable that you can't do something with. It's about defining a function and saying what it plans to do with the parameters. Here, I'm making a function f that takes a pointer to a double, but it says I want that to be a pointer to a const double. You can think of this as saying, I need you to give me a pointer to double, but I promise I won't use that pointer to change what's in your double. I just want to look at it. I can still use that pointer. So down here, I made up some code for computing the area of a circle given a radius. So D is a pointer to a double. So whenever I want to get the double it points to, I have to dereference it. And then I multiply that by another copy of whatever it points to. So there's a lot of stars here. These two are doing dereference. This one's doing a multiply. And I'm multiplying by an approximation of pi and returning that. This works just fine. It works particularly well with arrays. You can stick the word const on an array. You can read this as A is an array of const integers. So now I'm taking your array, but even though I'm taking it by reference, and normally that means I could change what's in that array, this const is like a way of promising that you're not going to do that. You're saying what you plan to do with the array. This would still let me print out what's in the array, but if I tried to cheat, the compiler is going to complain here. So think of const as a way of communicating with client code, telling them what you plan to do with the parameters that are passed in. You can always add a const without a typecast. So if you had an int pointer and you wanted to say, oh, pretend that's a pointer to a constant int, you can do that without any kind of typecast. You can always go from a less restrictive type to a more restrictive type. And a const int, a pointer to a const int, you can't do as much with that. So the compiler will let you add const. But going the other way requires a typecast. All else being equal, you should use const wherever you can because of what I just said. You can always go from a non-const pointer to a const pointer. It doesn't require anything fancy to say, oh, I don't need to do as much with that pointer. But going the other way requires some work. So given a choice between defining a function that takes a pointer to an int and one that takes a pointer to a const int, well, if you don't really need to change the int that points to, you might as well define it this way. Because if someone wanted to use their function and they had a pointer to an int that wasn't const, well, they could call either of these functions. But if all they had was a pointer to a const int, they couldn't call this function that expects a non-const int pointer. They can only call this one. So because this function can be used in more cases, you might as well use const wherever you can. We'll say a program is const correct. if it always uses const on pointers when it can, at least in function parameters. And the compiler will worry about, if you start using const on functions, the compiler will start worrying about making sure that you're not cheating anywhere like this. And here's an example of what I mean by that. And I've said this a little bit. If you say, I take a pointer to a const double, and then you try to do something sneaky, like you go in and try and dereference it and change that double, you're going to hear from the compiler about this. It'll try to make sure you respect the const that you promised on this function parameter. So here the compiler is trying to help you catch mistakes. But remember, const is just part of the type. And I said a couple of times, well, you can change the type with a typecast. So if you wanted to lie to the people who are writing the code that was going to use your code, if you wanted to cheat, you could do it, and it's no harder than a typecast. Here I made a function, and it claims that it wants a pointer to a double, and it claims I'm not going to change your double. But then inside the function, I take that pointer and I strip off the const by casting it to just a plain old pointer to a double. Some people call this casting away const. And I would say, well, you can do this because it is part of the type of that, but you shouldn't do this. At least if you're trying to write a function that other people can effectively use, you should tell the truth about what that function plans to use with data. This, well, const on a type is something you can sneak around, but it's something you should try not to sneak around. Imagine that this helps cooperative programmers to know what they're planning to do, and someone who is trying to do this is probably not being a cooperative programmer. That gets us through all our material for this lecture. You'll have a quiz for this, but it'll be online. So we covered all the material we were supposed to, so hopefully you're in good shape for that quiz. I've still got one more lecture to record, and then I'll see you next week. Have a good week.